Thank you very much for attending my presentation. My name is Kelvin Shear. I'm a system professor in the Department of Material Science and Engineering at Texas A&M University. My presentation title is on the dynamic recrystallization or lack thereof in shear bands at high rates. The work was really done by a previous postdoc in our group, Dr. Xiaolong Ma, who is now a permanent staff at PNNL. The work is also in collaboration with Professor Dinaka Sagapuram in the Department of Industrial and System Engineering at Texas A&M. I'll just use one slide to quickly introduce you what shear band is like. When we plastically deform a material, in many cases, we do not get uniform deformation. In this video here, you can see shear banding forming in the deformed soil sample. One common feature of shear banding is outside shear bands, you do not get a lot of deformation. The plastic deformation concentrated within the shear bands. Not only in soil, you can also observe shear bands in different metallic systems. In the example shown here, those are the shear bands generated in the pure iron under compression. Again, outside the shear bands, you don't see much deformation, and huge amount of deformation has taken place within the shear bands. The shear banding has been considered as an adiabatic process. This means the process happens so fast that the heat generated within the shear band cannot dissipate into the surrounding matrix. Let's look at the figure from a paper published by Rito and co-authors. So the blue curve depicts the stress. The stress level initially remains more or less the same. Then the shear band kicks in and there is a sudden drop of the stress. For the temperature, initially the temperature increases slowly, but when the shear banding kicks in, the temperature rises dramatically. This indicates there is a strong positive correlation of shear banding and increase in temperature within the shear band. The rapid increase in temperature has also been considered as a major cause to lead to recrystallization within the shear band, which we'll revisit towards the end of this presentation. Researchers from different groups have also carried out TEM investigations to look at the microstructure of shear bands. Here are some examples from the literature like titanium, copper, and Ti-64. Looking at the first example, the titanium example, the region outside the shear bands, you can see single crystals depicted by the sharp spots in the diffraction pattern. And for the grains within the shear band, the crystals have turned into nanocrystalline, giving you the ring pattern. In the shear band community, the formation of those nanocrystalline grains is attributed to the heat and the localized deformation leading to the dynamic recrystallization. Similar observations were also made in copper and the Ti-64. In both cases, within the shear bands, you see rings telling us the grains has turned into nanocrystalline. However, within the shear banding community, people also realized the temperature increase in some of the cases is not high enough to trigger recrystallization. Therefore, some arbitrary parameters have been introduced in mechanics models to explain the observed dynamic recrystallization. The question we ask ourselves is that, is dynamic recrystallization really the dominant mechanism for shear banding formation? To answer the question, we collaborated with Professor Dinaka Sagapuram's group, who specialize in cutting. Here is the experimental setup. You have the blade here, and as you feed material towards the blade, a metal strip can form. One special feature about titanium is when you cut titanium, instead of forming a smooth metal strip, you get this serration. Dinaka's group then did optical microscopy looking at the cross-section of this metal strip. After mechanical polishing and etching, they saw those bands in the titanium metal strip. Between the bands, the intrinsic or original microstructure is more or less retained. This tells us a lot of deformation happened within the bands, not between the bands. On the right is an SEM image, and micromarkers or the scratches were placed on the metal before doing the cut. Again, you can see a sharp or abrupt disruption of the continuity of those scratches at the shear bands. We then did characterization on the titanium metal strips. The first thing we did was EBSD. This, by the way, is the top view of the metal strip instead of the side view. Again, you can see that between the shear bands, you can resolve the microstructure very nicely, but you cannot resolve the microstructure within the shear bands. This is because there's so much strain stored within the shear bands, which makes the counts really bad in EBSD data. Here is a TEM micrograph that captures a shear band as well as the regions outside the shear band. When we did electron diffraction in the region outside the shear band, you can see individual diffraction spots telling us they are more or less still like coarse grain structure. Then within the shear band, you see the diffraction rings that tell us there are a lot of nanocrystalline grains within the shear bands, which seems to support the dynamic recrystallization hypothesis we mentioned at the earlier part of the presentation. As a TEM microscopist, we know that the diffraction contrast in TEM is extremely sensitive to the exact tilt of the crystal. Even 1 degree of reorientation can lead to a dramatic change in the contrast. In order to have a look at the shear band closer, we used a technique called Precession electron diffraction, PED, to further characterize the microstructure of the shear bands. In PED, there is a beam that precesses on the specimen, and underneath the specimen, we collect the diffraction pattern. The beam also rasters on the specimen, working in the same principle as SEM or STEM. The signal will be collected pixel by pixel. For each pixel, we collect the raw data, and the raw data will be compared to the simulated data to give us information on the crystal face as well as the crystal orientation. The example here was provided by Professor Paul Rotman when he was a PhD student with Professor Kevin Hemke at Johns Hopkins University. Paul now is a faculty at the University of Kentucky. What you look at here is a deposited thin film, copper thin film, then slightly annealed. The color tells the orientation of each grain. If I draw your attention to the scale bar is only 100 nanometers, so many of the grains are tens of nanometers in size. This is way beyond the resolution limit of EBSD. Hence, you can also consider PED as TEM-based EBSD. And we applied PED to study the microstructure of the shear band in titanium. The micrograph you see here is a virtual bright field image from PED. This is very similar to the regular bright field TEM image. Within the shear band, you can see many nanocrystalline grains. Here are a few examples, like here, 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 and here. One thing that really surprised us was when we saw the orientation mapping results. When looking at the orientation maps, we don't see these individual grains anymore. Instead, we see much coarser grains in the micrograph. The figure in the middle highlights the crystal orientation as well as high angle grain boundaries in the shear band. Here, we don't see these small nanoscale crystals anymore. But when we turn down the low angle grain boundaries, we start seeing these small crystals again. For example, like here and here. In the virtual bright field TEM images, they correspond to the dark grains. What this tells us is those nano grains we observed in the bright field TEM image as well as the virtual bright field TEM images, they are not separated by the conventional high angle grain boundaries. they are separated by the low-angle grain boundaries. What this means is to form those nanocrystalline grains is not formed by the conventional dynamic recrystallization mechanisms, where the dislocations accumulate and new grains of a brand new orientation forms in the microstructure. Rather, it's a top-down grain refinement process. The formation of those nanocrystalline grains is not a result of heat, but more a result of the crystal fragmentation. One may argue that if we are only getting a lot of low-angle grain boundaries, why do we see diffraction rings, which seems to be continuous, covering a large range of crystal orientations? To address the question, we drew a line in the shear band to look at both the point-to-point misorientation and point-to-origin misorientation. The blue line depicts the point-to-point misorientation. For point-to-point misorientation, the difference or the misorientation does not change dramatically. Maximum is only 5 or 7 degrees. But the small point-to-point differences can accumulate and lead to a large point-to-origin difference, as shown by this red curve here. Only about 500 nanometers away from the origin, and you already see the accumulative effect of 20 degrees misorientation. This is why in diffraction pattern we see the ring patterns. For those who are familiar with titanium, we know alpha titanium has HCP structure. This tells us not only dislocations can contribute to the plastic deformation, deformation twins can also be prevalent in the deformed microstructure. We also know for HCP crystals, there's extension twin and compression twin. We'll look at those one by one. Let's look at the shear band first. When examining the grain boundary misorientation histogram, you can see there is a peak around 60 to 64 degrees, and this misorientation corresponds to the compression twins in HCP crystal structures. This tells us the compression twins are also present in the shear band. Interestingly, if we look at the regions outside the shear bands using the EBSD data, and also plot the grain boundary misorientation histogram, you see a peak around 86 degrees. The 86-degree misorientation corresponds to the extension twins in HCP crystals. In most of the HCP crystals, the compression twins are more difficult to activate. What this tells us is within the shear bands, the energy is so huge and the stress level is so high that it's able to activate the compression twins. Then what are the implications of having compression twins in the shear band on its microstructure? What we believe is they will also contribute to the crystal fragmentation. So within the shear bands, the reorientation was facilitated by profuse dislocation activities and compression twins. There are 3 takeaway messages from this study. First is dynamic recrystallization, especially the conventional way how we view dynamic recrystallization, may not prevail in the microstructure of shear bands formation. For the classical dynamic recrystallization, heat is important to nucleate and grow those new grains. In our study, we demonstrated for some material systems, the crystal fragmentation alone is able to create the nanocrystalline-like structure. Therefore, in some of the shear band mechanics models, we don't need to introduce the arbitrary parameters to account for the lack of temperature to cause recrystallization. Second, in titanium, the shear band microstructure evolution is primarily dominated by the deformation-induced grain refinement, driven by substantial twinning and dislocation activities. Both dislocation activities and deformation twinning are important, contributing to the nanocrystalline appearing microstructure in the shear band in titanium. Third, this work urges the community to re-examine the microstructure obtained in shear bands of different materials. What we speculate is the melting temperature may play a big role on the final microstructure. For high melting temperature materials like titanium, the heat does not play a huge role, but for magnesium and magnesium alloys, which have low melting temperature, maybe the classical dynamic recrystallization mechanism still dominates the shear band formation. That concludes my presentation. Thank you very much for your attention.